this was comparing, as a refresher, right, these three different collapse modes. And so we already went through the energy method to identify which one is going to be the true mechanism for collapse, right? And that's the one that generates the lowest value for P to cause collapse. So then I said that we can verify this with equilibrium, right? And that involves plotting the shear moment diagrams. And what we're looking for is we want to make sure that in the true collapse mode, there won't be any value of moment in the entire distribution that exceeds the ultimate moment, right? So for that first mechanism where you have the plastic hinge at the fixed end and the plastic hinge at the center, here's your free body diagram of that collapsed condition. And then from that, you can calculate the reactions, RA and RB, right? We're assuming, well, we know that M is equal to MU at the plastic hinges, so that takes care of the fixed support. And then from there, you can draw your shear and moment diagrams. Since this moment diagram has a value that exceeds MU, that says, okay, this is not the correct mechanism, all right? Similar for the second mechanism, right? The process is very similar. We just have a different values for PU, right? And we have a different location for one of the plastic hinges. So we'll get different results for RA and RB, different shear and moment diagrams. In this moment diagram, though, there's nothing that exceeds the ultimate moment MU throughout the entire distribution. So this confirms that we have the exact solution. All right, and I'm not going to go through the whole process for that last one, but it would be similar, right? You would assign the values for that we solved for. So you would set P equal to, this would be 6 MU over L. So 2P would be 12 MU over L. And then you would go through, and this time you're calculating the reactions at A and B as well as the end moment, right? And you would find that the end moment has to be equal to 6 MU, right? And so just from that, you know that this is not going to be the correct collapse mechanism since we're exceeding MU by a lot. I don't know how much you need to see. we're almost done with that. So the next set of lecture notes then, lecture 32, we're going to apply this to frames, right? So it's called frame limit analysis. And what we're going to look at first is this frame that's pinned at the base. So with a point load at the center of the beam. All right, so this is indeterminate by 1 degree. And remember, what we are after is the value of PU that will cause collapse. Just say find PU. In order to do that, we're going to assume that the moment is mu throughout. Again, in reality, there will be a distribution, but we also know that in reality, in the true mechanism, nothing will exceed mu. So in reality, mu only occurs at the plastic hinges. All right, so with this load and this configuration, we can have a plastic hinge forming at the rigid joints, beam column rigid joints, and also at the location of the load. So this is one possible collapse mechanism. Or actually, for the vertical load, it's the only collapse mechanism. We'll look at side sway conditions later. So we have deflection delta and then angles theta. So for this mechanism, delta is equal to theta L over 2. And to investigate this more closely, we will look at just the beam, all right, since the columns aren't participating in this collapse mechanism. Isolate the beam. Something like that. So we have ultimate moment mu at each plastic hinge. And the directions that the moments are acting, they will always be in the direction that would work to restore the collapsed condition to the original uncollapsed state, right? So for the beam, our internal strain energy is going to be equal to 4 mu times theta. All right, so you can imagine the total rotation at that center hinge is equal to theta. So over here we have mu times theta. At this hinge we have mu times 2 theta, I should say. Right. Total rotation at that hinge is 2 theta. So mu times theta plus mu times 2 theta plus mu times theta gives us 4 mu theta. So I'll note here, this is the strain energy due to internal moment. MU, where MU works to keep the hinge lines vertical. Or, in other words, it works to resist the collapse. For the external work, we just have PU times delta, or PU times theta L over 2. So for total work, we set U equal to W. So we get PU is equal to 8 MU over L. So at the condition of collapse for this collapse mechanism, if we draw the expanded free body diagram, all right, we have PU is equal to 8 MU over L. On the beam, right, we're going to have shear at each end equal to 4 MU over L due to symmetric loading and supports. Right, I'm going to go ahead and transfer that through. So that will transfer to the column. And then in order for equilibrium to be satisfied, right, so we would have moments and horizontal forces as well. So that would end up being on the column MU over L to the left at the bottom of the left column, and then to the right at the top of the right column. That would transfer equal magnitude opposite direction to the beam. And then to the other column. Right, and we have those horizontal forces because this is not a simply supported frame. It has pins at both supports. So we'll have horizontal reactions there that oppose each other. We also have end moments at the rigid joints. And we know that's going to be MU, right? And those are the directions that MU will act on each member. So I kind of wrote those in an order that may be less intuitive. It may be more intuitive to first note that we have the moments, MU, at the locations where the plastic hinges are, all right? And this is, again, this is for the whole frame. So if we want, we could also break it up at this plastic hinge, right? But we don't need to do that to draw the moment diagram. So for purposes of drawing the moment diagram, we just need to separate the individual elements. And we know we have MU at those joints. So from that, right, and then knowing the vertical, we can just isolate this element to obtain this horizontal reaction. And then from there, we know this has to be the same, and then we can work that horizontal force through. Right. All right, so now that we have the expanded free body diagram, we can go ahead and draw the moment distribution. So as a refresher, right, for a beam, our positive moment convention is counterclockwise on the right side and clockwise on the left side. To apply that to a column, we would just take this image and rotate it 90 degrees counterclockwise. So our positive moment sign convention for a column looks like this. So for the columns, those are easy. We have 0 moment at the base where the support is pinned, and then that's going to just increase linearly to a value of negative mu at the rigid joint. For the left column. On the right column, it's going to be positive mu. For the beam, we start off with a negative moment at the left end, and then that's going to increase linearly to a positive mu at the center. And then that will decrease linearly to another negative mu. All right, so we can confirm that this mechanism is exact. Since the maximum moment is mu. But there's another possible mechanism, right? So we could potentially in a frame have side sway, even if there's no horizontal force applied. If side sway occurs, then the mechanism that could cause failure would be one where one of these joints maintains a 90-degree angle, right? So either the left beam column joint or the right beam column joint. And with that condition, right, that would mean you'd have a plastic hinge at the center where the load is applied, a plastic hinge at one of the beam column joints, and then side sway, right? So these pins are not preventing rotation at all. They already basically are a hinge. So down below, I'm gonna summarize the process, and then off to the right over here, we'll go through the math, right? So here, once that applied load reaches PU, right, it causes collapse. It's going to form a hinge at the center. And since it's at the center from the geometry, know that delta is equal to theta L over 2. And if we are maintaining that one of these rigid joints keeps its 90-degree angle, then that means that the frame has to sway by angle theta. So then at the hinges, we have our total moments times our total angles for the internal strain energy. All right, so we'll calculate our internal strain energy then. U is equal to mu times 2 theta. All right, so that's from this hinge here. All right, the total angle is 2 theta at that location, and we have mu. And then from this hinge at the beam column joint, all right, we also have 2 theta as our total rotation at the joint, right? We have a theta from the beam and a theta from the column. So our total internal strain energy is the same. All right, so again, these are from each plastic hinge. And our work is equal to P delta again, right, which is still P U times theta L over 2. So setting our internal strain energy equal to external work, we get PU is equal to 8mu over L. And the moment distribution is going to be the same as it was without side sway, right? So that means that either of these 2 mechanisms can occur unless side sway is prevented. So, and that can be accomplished through bracing. Because this frame, right, on its own, it's stable, right? It's a stable frame with rigid joints and pinned supports at the column. But if side sway occurs, right, in this collapse mechanism, that's one way it could fail. All right, so now we'll go through another example. This time we have a frame that has fixed supports at the base and a lateral load applied at the top of the left column. So in this scenario, all right, it's more indeterminate than the previous frame, so we need more hinges to occur, right? In the previous frame, that previous frame was 1 degree indeterminate, but we had one mechanism that used 3 hinges and one mechanism that used 2 hinges, right? So really with the side sway option, we only needed 2 hinges to occur. In this frame, we need more than that. So we can have a hinge developing at the fixed supports, and we can have hinges developing at the rigid joints. So if we assume those 4 hinges, then I'll sketch the collapse mechanism over here, right? We would have side sway due to the horizontal load and the hinges at the base. All right, so I'm gonna also sketch a vertical line there. So this distance, delta, all right, is the total distance that the frame sways laterally. We're going to have mu at all the hinges working in the direction to prevent the collapse. And if we say the angle of sway is theta, then delta is equal to theta times L. All right, so we have our thetas noted on here, and that's going to be the same on the other side. So we have 4 hinges, and at each hinge, we have mu theta. So our total internal strain energy is 4 mu theta. External work is P delta, which is P theta L. So setting our internal strain energy equal to external work, we get Pu is equal to 4 mu over L. So going through and applying this information to our free body diagram for all of the elements, we say, all right, we have our P, and we just said that's equal to 4 mu over L. All right, we also have our moments, mu. All right, and then going through this, this would result in actually horizontal reactions at the base of 2 mu over L each. And so you would have a net shear at the top of the left column of 2 mu over L acting to the left. Right, over here it would be 2 mu over L acting to the right. Transferring those to the beam. That beam is in compression, which makes sense. And then vertically, we would have vertical reactions also equal to 2 mu over L at the base, equal magnitude opposite direction to resist overturning.
Bottom left horizontal force is not equal opposite as the top one.
Here?
Left base.
It's supposed to be to the left, yep.
And so is the top.
Yep, because then you have equilibrium on this free body diagram with this force acting to the right.
Sure.
Yep. Yeah. I know, at an initial take, it looks wrong. All right, so if we sketch the moment diagrams, we would get something like this. All right, where we have mu at the top and the bottom for the columns. And those would be identical. And for the beam, we would start with a positive mu and end with a negative mu. And since the moment distribution does not exceed mu at all, then we know we have the exact mechanism. All right. So the next example we're going to look at is going to be a circular beam. And an indeterminate one at that. So we have a half circle here with an applied lateral load, all right, at the top. So first we're going to assume that the material is elastic plastic and forms hinges at the fixed support at A and also somewhere between B and C, all right? So that's going to be our initial guess of the collapse mechanism. The other possible collapse mechanism would be a hinge forms at A and a hinge forms somewhere in span AB. So based on this, our assumed collapse mechanism, all right, based on the configuration and loading, we would assume that we have mu at A. And we know we're going to have a vertical reaction, we'll call that Cy, at the roller support at C. So for equilibrium to be satisfied, we're just going to solve for Cy in terms of mu and pu. All right, so say mu minus pu times moment arm of R plus Cy times a moment arm of 2R. All right, so I'm summing moments about A. That's equal to 0. So Cy is equal to pu over 2 minus mu over 2R. All right, so that was just looking at the entire structure, assuming mu over here at A. Now, if we assume our second hinge forms in BC, we'll place that hinge somewhere in BC and isolate the right side of that hinge. All right, so if we sum moments about the hinge, then we have negative mu plus cy times its moment arm to the hinge, which is this distance here. That's going to be r times 1 minus cosine phi, right? So I'm using phi to measure the angle there. So we have r, let's see, mu plus cy times r, and then 1 minus cosine phi is equal to 0. So we have mu, and now I'm going to substitute in our expression for cy in terms of pu and mu. So we have mu is equal to pu over 2 minus mu over 2r times r times 1 minus cosine phi. Solving for pu, we get mu times, in parentheses, 3 minus cosine phi divided by r, and in parentheses, 1 minus cosine phi. So I'll just note phi specifically is a variable here, right? It's the angle to the hinge in BC. Okay, so we've gotten this far. How do we know if this is actually our collapse mechanism, though? We want to find out if there is any extreme within this range, right? So we have an expression for pu in terms of mu and phi. So we'll use that. So we can take the partial derivative of pu with respect to phi and set that equal to 0 to see if there's an extreme between b and c. So we have sine of phi times 1 minus cosine phi minus 3 plus cosine phi would be that partial derivative. Set that equal to 0. So that comes to 2 sine of phi is equal to 0, which means phi has to be equal to 0. When phi is equal to 0, that's at point C. All right, but that's a trivial result because point C is a roller support, so it can't develop any moment there, right? So we know the moment there is always going to be equal to 0. There is no extreme at point C. So that means that there's not going to be a maximum moment in span BC. So we'll have to look at this hinge occurring in span AB instead. All right, so now putting our hinge in AB, free body diagram looks like this. We're going to use the right side of that free body diagram, And why do we have to consider these spans separately, by the way? Why couldn't we just figure this out with putting the hinge in one place?
Because there's not an equation to define that distance to our hinge for the whole range of feet.
Well, sorry, can you say that one more time?
We couldn't have an equation to define our distance to our hinge from the sea for the whole range of feet.
Right, yeah, we can't have one equation that covers the whole range because we have the applied load at B, right? So that kind of breaks it up into two distinct segments. So if we sum moments about the hinge and consider the right side, then we'd have negative mu plus cy times the total moment arm to the hinge, which now is this whole distance. All right, so that's going to be r plus r cosine theta, right? If we define theta as 180 minus phi. Minus pu times r times the moment arm. Let's see. So we're looking for the moment arm of p with respect about this point here, right? So that's this distance, which is going to be r times 1 minus sine of phi. So we have mu is equal to, in parentheses, pu over 2 minus mu over 2r. And that is multiplied by r and 1 minus cosine of phi. Let's see. I'm going to come back to that in a second. And then minus pu times r and 1 minus sine of phi. So we end up with pu is equal to mu over r times, in parentheses, 3 minus cosine of phi divided by 1 minus cosine phi minus 2 times 1 minus sine of phi. All right, so then over here I have some notes that will help with this as well. So cosine of theta is equal to negative cosine of phi. Sine of theta is equal to sine of phi. So I made a couple of substitutions in there. Okay, questions so far? All right, so now we have an expression for PU with the plastic hinge condition in span AB. Continue this and finish this process out. So we'll check for the location of maximum. So what we're looking for, right, when I set up here no maximum moment in BC because we didn't find a location where phi is equal to something between B and C, right? So what we're solving here is for a value of phi that would locate the plastic hinge, right? That's where we would have a maximum value. And so since we know that the plastic hinge will have the maximum moment, that's why I referred to the maximum moment not being in BC, because there's no plastic hinge in BC. So now that we're looking at AB, let's find out where we would have a maximum from that equation. So carrying that out, I will spare you from the math. You'll get the result. Phi is equal to 107.5 degrees. So that corresponds to a PU of 2.73 times mu over r. And that means that our vertical reaction, Cy, is 0.865 times mu over r. And so then we want to plot the moment distribution, right? We can do that. So we'll consider span BC. So this is where phi is between 0 and pi over 2. So we have our moment is equal to, I'll write this as moment as it varies with angle phi, is equal to 0.865 times mu times 1 minus cosine phi. And then for span AB, where pi over 2 is between, or phi is between pi over 2 and pi, we have our moment is equal to 0.865 mu times 1 minus cosine phi minus 2.73 mu times 1 minus sine of phi. So if we go ahead and plot some points, we have 0 at C, which is the roller support. Right, at pi over 4, we would get a value of 0.25. At pi over 2, we would get a value of 0.865. And then somewhere between pi over 2 and 3 pi over 4, we would get a value of 1. I'm not quite getting the right shape here. It's going to be something like that. And then at 3 pi over 4, we would have a value of 0.677. And at pi, we would have a value of -1. So the trend would look something like this. Right, where those are curved lines, not straight lines, but something like that. All right, so the moment distribution plot confirms that nothing exceeds mu, right? So we're plotting m over mu in this case. So we have the correct collapse mechanism. Any questions? Okay. So I know we're out of time. I will be posting a homework assignment today, so keep an eye out for that. It'll be on failure, and yeah, collapse mechanisms and stuff. So.
When will that be due?
Good question. I think, look at our schedule here. So I have it noted as being due on Friday. I think I'm gonna keep it at that because the other option is to have 2 homework assignments due the week after Thanksgiving, and I don't think you want that. Yeah.
Is the homework time gonna be assigned before break?
Yes, I will assign that before break. Mhm. All right. Well, thank you all for your attention. I'll see you on Wednesday.